The next unit that we're going to cover involves what are called systems of equations. Now, up until this point, all of or most of the problems that we've talked about in this series of videos have dealt with one equation, and that one equation can have either one or two variables. So, for example, every time I do that, like start writing, it's not... This doesn't work. And so we might have an equation like this, like 2x plus 6 equals 10. And that is a linear equation in one variable. And typically you would need to solve that equation. And that could come from a written description of some kind of physical reality. Okay. And you would solve that. And I'll go through this really quickly. So if you went to solve it, you would get x is equal to 2, so I subtracted 6 and then divided by 2, and I get x is equal to 2. And it's important to remember this, that the solution, so we go and find the solution, that what we actually found there was the value of the variable that made the equation true. And so we have 10 is equal to 10. And that's what we're finding when we're solving an equation. Now, we've also looked at equations in two variables. Okay? And so we might have something like y equals 2x plus 4, and that's a linear equation in two variables. And typically with a problem like this, you might be asked to identify the slope, identify the y-intercept. You might be asked, like this one is what we call solve for y, because the y is by itself. You might be asked to solve for x. Okay, that would mean do some algebra and get the x by itself. You're also often asked to graph an equation like this. And if we were to graph it, the y-intercept is 4, and then the slope is 2 over 1. And I want to point out what the graph is. And we talked about this when we did graphing lines, but we are able to graph the line by finding only 2 points. And in this particular case, we have the point 0, 4, and we have the point, what do we have? The point 1, 6. Okay, are two of the points, but there are more points. I mean, like you can put, like I'm putting some dots here. In fact, there's an infinite number of points. Now, it's important to remember too what that line is and what these points are. These are pairs of values that when plugged in for x and for y in the equation will make the equation true. So for instance, we might have 4 is equal to... Let me do this in a different color. So we'd have 4 is equal to 2 times 0 plus 4. So 4 is equal to 0 plus 4, or 4 is equal to 4, which is true. But it's not the only point that works. So in this type of linear equation, there's only one value that works. If you plug in anything else for x, you will not get a true statement. But when you're dealing with a line, you actually have infinite values that would work. And so we can look at the other point. We can say 6 is... Oh. Okay, I'm sorry. I don't know what happened. Well, I do know what happened. I got a notification on my iPad, and I went to grab the next color, and I accidentally tapped on the notification, and then it kicked me out of the program. So what am I doing here? So we have 6 is equal to 2, and now we're going to plug in the 1. And so we get 6 is equal to 2 plus 4, and 6 is equal to 6. And so, and there's more, there's infinite numbers, pairs of numbers that you could plug in and make that equation true. And that's pretty much what we've been looking at. Now, in real life, though, there are often variables that are bound by more than one relationship. And so there are actually multiple things going on, and the variables have to satisfy more than one equation. So in this case, in order to find a solution, there's an infinite number of them because they only have to satisfy that equation. But what if we had some other relationship, and the x and the y also had to make that other relationship true. How would we choose from among all of the possible solutions? So I'm going to give you a quick example of a situation that is like that, but we're not going to start with solving that particular kind of problem, just because we're going to go through different strategies to solve them, and it won't be a good, like the strategy that we're doing today won't be a good strategy for it, but it'll give you an idea of what kinds of problems we were looking at in this particular unit. Okay, so this is a total of $9,000 is invested in two accounts, one paying 5% annual interest and the other paying 6%. The combined annual interest is $510. How much is invested in each account? So there are actually two relationships at play here. One is the amount of money total, and the other is the amount of interest. So if I call, let's say, X equals the amount in the first account, and Y equals the amount in the second account, then we could write what's called a system of equations as follows. If I take X and I add it to Y, that should be $9,000. Okay, because it says the total amount of money that's invested is $9,000. So the amount invested in the first account plus the amount invested in the second account should be $9,000. Now the other has to do with the interest. Okay, and we know that the first account is earning 5% interest. Now, I don't want to get into in this lesson like how you find percent. Hopefully that has been covered at a previous like level of math class. I am aware that that's not always the case, but you know, if you have a question like that, you can always comment on the video and like ask, and I'd be happy to try to address that. But here's the reasoning here: 5% as a decimal is 0.05. And if you want 5% of some money, that of becomes multiplication. And so what we would have is 0.05 of is multiplication, and we want 5% of the amount invested in the first account. And then the other one is the same thing except, with 6. And so 6% is 0.06. Of is the multiplication, just a super useful thing to know. And then we want 6% of the amount in the second account. And now, this is what is called a system. Okay? And that's important to know so that you know when you're looking at this particular kind of problem. And this is how I define system for my students. A system is two or more equations with the same variables. So for example, 3x plus 2y equals 4 and negative x plus 3y equals negative 5. So this would be two equations with the same variables x and y. Now, a couple of like facts about systems of equations. If you want to be able to solve them, you cannot have more variables than you do equations. So you can have it, notice I said here two or more. Usually in Algebra 1, we stop with systems of two equations, and then when you take Algebra 2, you would start to engage and interact in systems of 3 equations. And you get those skills in place. And honestly, the place where I used them the most was in physics class. So, you end up, I think like the worst one I ever did was like 7 equations with 7 variables. Don't worry, we're not going to look at that now. But it's important to know when you're looking at a systems problem. And again, they're variables that are controlled by more than one relationship. And so you have like x and y, and they need to be related this way. If you take 3 times the value of x plus 2 times the value of y and add them, you need to be able to get a 4. If you take the opposite of x and you add 3 times the value of y, that should give you -5. And what we're looking for when we're solving them, okay, so we want to know what we're trying to find. We're looking for the values of the variables that make all the equations in the system true. Okay, so it is important to know this. You want to know the definition of what a system is, and you also want to know the definition of what a solution is, because otherwise you don't necessarily know when you've done it. Now, I want to go back to this slide for a moment, because the strategy that we're looking at today is what's called the graphing strategy. When you graph a line, you are creating a picture of the points that make that equation true. Okay, that's literally what you're doing. And so in theory, if I had like a nice neat graph here, I could pick any one of these XY pairs, any of them, plug them into that equation and get a true statement. Okay, that's literally what the graph of a line is. Now, when we're looking for the solution to a system, we're looking for the variables that make all of the equations true. So it's not enough to just graph one equation and find that relationship or that picture. You need to graph both equations. So here's the idea. If I graph the first equation, that's all the points that make first equation true, because that's what a graph is. All of these points will make the first equation true. If I graph that equation, these are all the points that make the second equation true. And what are we looking for? We're looking for the values of the variables represented by the points that make both, in this case both, because there's only 2, that make both of the equations true. Where will that be? That will be at the point of intersection. That point right there works for both the purple line and for the green line. So the graphing strategy works like this. You graph both of the lines, and your answer to the problem is the point of intersection. Some teachers will make you write it like an ordered pair. Other teachers will make you write it as 2 separate numbers, like x equals y equals. Both are correct. You just want to be listening to whatever your teacher's expectations are. Okay, so we're going to look at an example, and I'll show you how it works. And then I'm going to do another example actually with this system here. And we'll talk a little bit about like the disadvantages of this method. So the system that we're going to solve is this. We're going to solve x plus y equals -2. And we'll make that one color. And then we're going to do 2x minus 3y equals 9. So you have 2 ways that you can graph this. You can build your table and plot the points to know where the line is supposed to go, or you can put it in slope-intercept form and graph using the slope and the y-intercept. Not one method is not better than the other, especially in a case like this where they are both given to you in standard form. So as a quick review, like we'll kind of do this. We'll build a table, pick nice easy numbers, okay? So we'll pick like 0, 1, 2. And I'm going to do the scratch work over here. So 0 plus y equals -2. So y would be -2. 1 plus y equals -2. So we'll go ahead and subtract 1, and y is equal to -3. And 2. Actually, that's, well, I guess it's fine. 2 plus y equals -2, and we're subtracting 2, so y is equal to -4. I was going to say, it's getting a little too negative. Why don't we go in the other direction? But honestly, it doesn't really matter. All right, so plotting these, we have 0, -2. We have 1, -3. And 2, -4. And we really want to do the best line possible here. So what I'm going to do, and we don't have to do this to graph a line, but we do need to do it if we want our line to be really accurate. You can see exactly what the pattern is here. We're going down one, right one, down one, right one, or up one, back one, up one, back one. And so what I'm going to do is just plot a lot more points, not because it's required to be able to graph a line, but because I know it's going to hold my line nice and straight, because I tend to wobble, and at least I can see where those points should have been. Now, if you wanted to do this by putting it in slope-intercept form, here we would subtract 2x from both sides, and that would give us negative 3x. And then you could write 9, you could do this, you could do 9 minus 2x, okay? But probably you want it the other way, so negative 2x plus 9, just so it's in the order that you expect it to be in. And then we have to divide everything by negative 3. And we get y is equal to, now, just like as a review, like we want to be careful here. A negative divided by a negative is going to give you a positive. And then positive 9 divided by negative 3 is negative 3. And so this line has a y-intercept at negative 3. Oh, crud, I copied the problem wrong. I was like, wait a minute, this doesn't seem right. I copied the problem wrong, only in one spot. So here's what you do when you realize you copied the problem wrong. You don't panic. You don't make a big deal about it. We're just going to go fix it. Hashtag teaching opportunity. So here's my mistake. This should have been a negative 9 instead of a positive 9. So what I'm going to do is going to sneak in that negative, which is going to make it a negative 9 right here, which means that this plus sign right here should be a minus sign. And then I have a negative divided by a negative, which is going to give me a positive. Okay, so don't panic. Obviously, I mean, if you've watched all of these videos, this is not the first time I have miscopied something. So it is what it is. And you don't panic. Don't make a big deal about it. You just roll with it, and you go back and fix your work, and it's not a big deal. So for this one, the y-intercept is a positive 3. So 1, 2, 3. And my slope is 2 over 3. So that's a rise of 2 and a run of 3. So I'm going to go up 2 and then over 1, 2, 3. And I'll do it again, up 2 over 3. And again, that just guarantees that my line is straight. Over here, I'll go down 2 and back 3. And I'll do that a couple times. And that guarantees that my lines are not going to wander across the page. Now, remember the reasoning here. The first line gives us a graph or a picture of all the points that work for the first equation. The second gives us a picture of all the points that work for the second equation. And the ones that work for both, which is what we're for, is where they intersect. So in my problem, that is right here. And you can express that answer as negative 3, 1, or you might say x is equal to negative 3, y is equal to positive 1. And those are the values of the variables that make both of those equations true. They're going to satisfy both of the equations. And you could go back and plug them in if you wanted to. Now, very quickly, because I don't want this lesson to get too long, I do want to go back to the other problem, which was this, 3x plus 2y equals 4, and negative x plus 3y equals negative 5. So this first one, I'll subtract 3x from both sides, and I get 2y is equal to negative 3x plus 4. And again, I'm just writing that in that order because it's nicer. And then we'll go and divide everything by 2. So we end up with a slope of negative 3 halves plus 2. And we go graph that, and it's no biggie. Down 3, right 2. Okay. All right. So far, so good. But watch what happens on this next one. On this next one, I'm going to add x to both sides. So I get 3y is equal to x minus 5. and then divide everything by 3. That is a 1x, so we end up with a slope of 1/3 x, and then this is what I want you to notice. The y-intercept is not what we would call a friendly number. And what this does is it makes it difficult to graph the line. So a lot of you would want to change this over to a decimal, which is what, like 1.6? 1.6 repeating. And the problem with that is that you can't be 100% sure that you've put your dot in the right place. And so when I go to graph it, I've got to put my y-intercept at negative 1.6 repeating. Maybe it's right about there. It's just not, it's just not great. Okay. And so when you go to graph it, there's a certain amount of inaccuracy with it. And so when I teach this strategy to my students, I try to make this point clear. We teach this strategy because it is a really important concept. It's actually a very powerful concept that can open up ways of solving things that you might not have thought of. In fact, when you get a graphing calculator, or if you have access to a graphing calculator app or something, knowing this idea can actually give you what I call the secret to solving anything. Okay, like it's very, very powerful, and it's worth teaching because of that. However, it is time consuming. Okay, so it involves multiple graphs on the same coordinate plane. And this is the big one. It is horribly inaccurate. If there's anything about your graph that like wobbles, or you get unfriendly numbers, or you have a system where the actual points of intersection are like huge numbers, like 10,000, those just become very impractical to try to graph. And so there are some very serious drawbacks to it. However, as I point out to my students, we can overcome that with graphing calculators and different apps that can overcome both the time issue and the accuracy issue. So very, very powerful idea, worth knowing, worth practicing. Just usually we only practice on like lines, and we practice on pretty simple lines. So that being said, on the next slide, you will find some problems to practice on, because they are time consuming for this and for some other lessons. I'm going to keep the number of practice problems a little bit smaller, but if you are doing this for your algebra class, hopefully you have some problems that have been assigned by your teacher, or you can access some more problems to work on to get some additional practice with this concept. Okay, here they are. First problem is basically reinforcing the idea of what a solution is. So are 2, -1 and -3, 2 solutions to that system, which is 3x plus 2y equals 4 and -x plus 2y equals -5. So like, are those numbers solutions to that system, or are those points solutions to that system? 2, 3, and 4 are to solve by graphing. So 2x plus y equals 4 and x minus 1 equals 2. X plus 3y equals, that's a sloppy shoddy equal sign there. Not totally sure that's better. X plus 3y equals 2 and -x plus 2y equals 3. And then number 4 is 2x minus y equals 2 and 4x plus 3y equals 24. And then number 5 is really asking to see if you can extend the idea to something that looks unfamiliar, to some like branch of math or piece of algebra that you haven't been taught yet. And so the question is not what are the solutions, but how many solutions does the system have? So you've got the black XY axis, and then there is a purple graph, and then there is a green graph on there. How many solutions does that system have? So pause the video, work the problems out, and then unpause to check your answers. Okay, for this first one, pretty much what you need to do is you need to plug the ordered pairs into each of the equations and see which ordered pair, if either of them, works for both, or perhaps both of them work. You might be able to deduce that if you know that these are systems of linear equations, that they can't both work. But the first one, when you plug in the 2 and the -1, for the first equation, you get 4 equals 4, and for the second equation, you get -5 equals -5, and so your answer would be yes. You would be expected to show this in the event that you were asked to show your work. The second one, you plug it into the first equation, and you end up with the false statement, -5 equals 4, and so the answer to that is no. You don't have to check the second equation, because the definition is that they're supposed to work for both. So as soon as it doesn't work for one, like, that's not an answer. This is very, very valuable on anything that is multiple choice, especially if you blank out on some of the algebraic strategies for solving systems. As long as you remember what the solution is, what it's defined as, you can do multiple choice tests really easily this way. Second one, I opted to solve these for y, to graph them. And so you can see my two graphs. Your graphs should be the same. Even if you did them a different way, even if you built a table or your algebra doesn't look identical to mine, your lines should look identical. These intersect at the point 2, 0, and some people will have you express that as 2, 0, and some will say x equals 2, y equals 0. I don't care for my students. I honestly don't care. They can present their answer either way for me. And then, as always, with any of these problems, pause it and look at the solution, correct your work if you need to. Now, this one, I opted to make the table. And the reason I opted to make the table is because when I started to solve them for y, realized that these do not have nice intercepts. And what I did, if you're wondering how I got such nice numbers there, is I actually picked a value for y, because y ends up being the trouble spot with this one, and then found the value of x that went with the y instead of the other way around, which you can do with lines. You cannot do it with every single function out there, but you can do it with lines. And so when you plug in y is 0, you can figure out x is 2. When you plug in y is 1, and then you subtract 3 from both sides, you end up with x is equal to -1. And so I did that actually the same way on both. And if you look at it, I actually stumbled across the answer when I was building my table. And so if this is any kind of assessment or test where you don't need to show all your work, you could actually stop. Like, the moment I got -1, 1 in the second table and -1, 1 pops up in the first table, then that point is common to both lines, and you don't have to go through the whole process of graphing them. Now, you were supposed to do it for this particular problem, so make sure that you have your graphs. They should look similar to mine. You might not have the work done the same way, and that's totally okay. And then the answer would be -1, 1, or x equals -1, y equals 1. But, be alert to stuff like that. This one, I solved them both for y. That's how I prefer to do it rather than building the tables. And again, my lines came out like this. You can, if you did it the same way, you should be able to check your equation compared to mine. If you got like your negative in the denominator, again, that doesn't matter. Like, when you go to look at your graphs should be the same. And these intersect at the point 3, 4. So you'd have x is equal to 3, y is equal to 4. If you feel like your graphs get wobbly and you're not 100% sure, because mine, like, they don't look like they're perfectly intersecting right at the point 3, 4. If you question that, and I actually did do this, I didn't do the scratch workout for it, but I went through this process here where I took the 3, 4 and I plugged it in, and I just did it in my head. A quick little, like, 3, 4, so 6 minus 4 is 2, and like 12 plus 12 is equal to 24, just to make sure, because my graph wasn't super great there. And then I just drew this one bigger. This is where you want to get into that larger concept of even if you've never seen a graph that looks like this, which you will at some point in Algebra 1, in Algebra 1. But now I'm thinking, like, maybe not. I didn't do it in Algebra 1. I did it in Algebra 2. But a lot of people do it in Algebra 1. And you know what? It doesn't matter. Okay. The graph is still the picture of all the points that make some kind of equation true. And this is the picture of these points. And so if you know the definition and you know you're looking for the points or the values that make both true, you would still be looking for the points of intersection And so this system has two solutions. Now, if you have just two lines, the two lines can at most intersect in one spot unless they're the same line, which we'll talk about that in a future lesson. But this is clearly not a line, and this particular system has two solutions. So the concept transfers over, transfers out to other things.